In May 1919, two teams of British astronomers fanned out to either side of the Atlantic Ocean, one in Brazil, one to the island of Principe, off the coast of Equatorial Guinea. They were there to photograph a solar eclipse. It didn't go great. The Principe team were able to take 16 photos, but only 2 of them had proved useful once they got them back to England. The Brazil team did a little better, I guess. They got 19 photos, but they found out once developed that all of these were somewhat out of focus. One of these Brazil photos is the one pictured on the screen. It took until November for the astronomers to deem their analysis complete and ready for a public unveiling. They convened a large meeting at the Royal Society on November 6, 1919, and invited many members of the press to attend. The fact that Newton's portrait hung on the wall gazing over these proceedings was lost on no one. This is the banner headline the London Times ran the next day, November 7th, 1919. It made Einstein an immediate worldwide celebrity, whereas before he was basically unknown outside of Germany or scientific circles. So, what's going on here? I'm fully aware that I just invoked Einstein's name out of nowhere there. As the opening title indicated, this is the lecture on general relativity, which is, most basically, a theory of gravity. It's also a bona fide revolution in scientific thinking. To my mind, the story of general relativity kind of grants access to 3 big questions. The first is kind of a more or less scientific question: what is gravity? That was really what Einstein was concerned with. That was what's consuming him for these several years he's developing the theory. But for us, with the benefit of hindsight, I'm also thinking about these other extra scientific questions. How do fundamental theories of science change? What is it like to do science? Now, the question you should be asking is, how could it be that this small handful of photos of an eclipse can lead to such an audacious claim that Newton's gravity is overturned, replaced with Einstein's idea? Basically, what the photos show is this. Einstein, as part of general relativity, is positing one of the outcomes of his thinking is that if I'm right, he says, here's the sun, here's Earth. And the reason they needed to photograph an eclipse was because they needed to know if some distant star shining light out in the cosmos. So here's the situation. You've got a distant star, here's Earth, and Einstein says if I'm right, then the light from the distant star, if it passes near the sun, its gravity, and this is the wacky revolutionary idea, will bend the starlight a little bit. And it arrives here at Earth and we observe it. It's on the photoplate, right? And what that means is it will appear as if the sun's gravity bends this light path a little bit on its way to Earth, it will appear as though the star is really back here. Now, what they're talking about, this is an angle, right? And what his prediction is about 1.8 or 75 arc seconds. To give you a little perspective, an arc second is what you get if you hold a quarter 2 miles away from your eye. So if you held this quarter 2 miles out, up in the night sky, it would subtend, or block out, 1.75 arc seconds of angle. Of course, to understand how one theory can replace the other, we have to think about the original idea, the one that gets replaced. Newton's universal law of gravitation is basically what gets replaced. And he says, force of gravity is proportional to the product of two masses over the square of the distance between them. Now, this works fantastically well for almost any kind of solar system level observation or prediction you want to make. It explains apples falling off trees, comets and planets orbiting the sun. But there was kind of a glaring problem with this as far as Einstein was concerned. And the problem was this idea of instantaneous action at a distance. That if one of these masses were to cease to exist, the other one would instantly stop feeling the force. Like if the sun somehow just blanked out, the Earth would immediately, in no time at all, instantaneously, start careening off on its straight line path that it would be on, according to Newton's first law, if it weren't for this force of gravity holding it in place. This specifically is a problem for Einstein because in the special theory, nothing is faster than light, which includes any signal that gravity would be transmitted through the universe. So this violates special relativity. Now, to his credit, even Newton in his day wrote a passage that was like, yeah, it's weird to just say everything happens instantaneously. I can't explain this. That's for others to figure out. But even more basic than all those problems, it might be striking you if you saw this equation earlier. Newton's theory of gravity, it's mass times mass over distance squared. If we're trying to argue that light is bent by the gravity of the sun, light doesn't have mass. So where is it going in this equation? This is why Einstein's idea was so radical. Another big thing giving Einstein reason to think this is a problem worth pursuing is that the field had this big kind of sticky spot they were dealing with called the precession of Mercury. Now, what is this? What's a precession? As will not be controversial to you, planets go around the sun. Here's our pal Mercury. And every time a planet goes around, it makes an elliptical orbit. And they're pretty much circular, but they're technically elliptical. Now, there is a spot in your orbit when you're closest to the sun. In this moment when you're closest, the shortest distance you are from the sun in your elliptical orbit, has this term, perihelion. So the thing is, you go around, you're close, you're far, you're close, you're far. But this thing, the perihelion, it would drift. Now, we gotta ask, how much does it drift? Are you ready for this? So this amount is going around and around that the perihelion moves, which means you're doing more like the spirograph thing as the centuries and the millennia go by. This was drifting 43 arc seconds per, ready for it, century. This is not a big number, but it was well established at the time. By the time Einstein came on the scene, this number was well known because the astronomical data that we could work with was that good. And it couldn't be explained away. There was this idea that maybe there was some sort of cloud of like invisible mass that was pushing it along, pulling it off its perfect elliptical path year by year. It's an interesting tidbit from science that people hypothesized there was this phantom planet that can't be seen. They named it Vulcan, and that's the reason the perihelion is drifting this much. The bottom line is that Newton's laws cannot explain this. Newton's theory, no matter how, they tried every which way, they couldn't use the theory to explain why this drift was happening. And as an aside, this planet Vulcan thing wasn't as crazy as you think. This like invisible mass idea, was something that was used to discover Neptune not so long before this. So Einstein, shortly after special relativity is published and gets known and is becoming more and more accepted, as crazy as it is with its time dilations and length contractions, he's unsatisfied that it has nothing to do with accelerated motion. And he's thinking about gravity, and he knows about the precession of Mercury, and he's unsatisfied that so far what was only then called relativity theory was so special and couldn't be applied to accelerated motion. So he's thinking about all this, and he has what has become known as his happiest thought. And his happiest thought is this. He sees someone, like a window washer, outside a window, and he thinks, what would happen if they fell and they were falling to Earth? Well, that's kind of a morbid, happy thought. But what he got to was this idea, and it's come to be known as the equivalence principle. How he explained it is this way. So say you've got a box. I mean, Einstein loves his thought experiments, right? He says, you got a box, you got a person in the box, and say they're on a scale. And here's the readout on the scale, right? Now, if you're in this box standing on this scale, it's going to read out your weight. It's going to read out how much gravity is pulling you down, pressing you into this sensor here. But if you've ever seen 2001 or any number of sci-fi movies where you're in space for a prolonged period of time and you don't want your bones to turn to jelly, there's a way to trick your body into experiencing this gravity, this weight. You can alternatively accelerate in the opposite direction. And if you're in this box, you can accelerate at a rate that would push you into the floor just as hard as the force of gravity of having the Earth under your feet would do. So Einstein says, if you're in this box and you've got no other way of knowing, if all you have is this scale, you can't tell the difference between the gravity-induced reading or the box accelerating up reading. And this is equivalence principle. And the reason Einstein got so excited about this idea was that this kind of put the problem of gravity like in his wheelhouse, right? And he says, well, if you're not, say you're not a person on a scale, say you're a light beam originating from one side and moving across to the other, if this is accelerating up, that light beam, if it's accelerating up fast enough, would experience some kind of drop-off. It would curve in its path as it moved across the accelerating upward box. But the kicker is, and this is what's hard to wrap your head around, equivalence, right? Gravity is acceleration. There's no, for the purposes of the light thought experiment, there's no difference between these two situations. Therefore, light will bend in the presence of a sufficiently strong gravity field. And if all that weren't enough, there's this other kind of outcome of special relativity worth talking about. Right. So Einstein, he's dissatisfied that special relativity can't talk about accelerated motion. And he's thinking about the special case of like very fast rotations. So let's say there's like a center of a circle and something is going to go around in a circular path really, really fast. If you were going sufficiently fast, any instant in time, you're kind of moving in a straight line. And if you were making this really fast circular trip and you wanted to lay out a ruler along the circumference,
end to end to end, this ruler right here, if this ruler were going very fast, some appreciable value of the speed of light, well, from Mary's talk, from special relativity, we know that this thing's length will contract. And if you lay it end to end, all the way around here, the measurer will report a larger circumference because all of these ruler contractions, it will appear that more rulers fit on this circle. But here's where it gets wild. If you did the same, if you laid out the same ruler to measure the radius, the same would not happen in this dimension. So this thing where like, okay, circumference over diameter will no longer equal pi. This is another key insight for Einstein, because it leads him to take the radical step to abandon Euclidean geometry. He says that for sufficiently accelerating systems, that under sufficiently large gravitational fields or large accelerations, this old Euclidean rule, you know, which is like so hard to even think about being wrong, it only works in regular three-dimensional space that's not moving, that's not undergoing relativistic motion. So this is another like difficult thing to accept. There's this old kind of riddle or a puzzle I was hipped to when I was about your age. And the question was posed to me. You leave your house, you travel 5 miles due south, and then you turn to the right and go 5 miles due west, where you see a bear, and you are frightened, so you run 5 miles north, where you return home. What color is the bear? You should pause now if you want to actually think that through for a while, because I'm about to spoil it. I'm about to give the answer. The answer is, the bear is white because you're at the North Pole. So what does this have to do with general relativity? Well, Einstein's thinking about the fast rotation, the relativistic circular motion, and how circumference over diameter is no longer equaling pi for situations like that. Like, he has enough insight. He famously is not the math guy. He's not the guy you turn to when you want some real good math happening. But he knows enough to know, like, there's other people dealing with problems of curved space, non-Euclidean geometry. And on a globe, if you know, as the puzzle says, go due south, and then you go west, and then north again, you're gonna feel like you made a triangle, but you didn't make a triangle, did you? Not in the common sense. Like, anyone measuring the angles made at these corners is gonna get 90 degrees for all those corners. Breakdown, right? Geometry broken. Euclidean normal planar geometry isn't working here. But that's not, okay, this is an analogy, right? So if you're on the planet Earth and you know you're on a sphere, you say, well, the problem is this is an arc, this is an arc, this is an arc. These aren't straight lines. You just dig a trench and you can make this a triangle and then everything's fine again. I ask you to suspend that thinking for general relativity and imagine like you're trapped on this surface, right? Like this is the only space you can be in. That's the point. Now let's think about that specific case of the fast rotation and how the circumference would appear to the fast-moving measurer to be bigger than it really is. So let's see how that jives with the spherical arrangement, or what would be called positive curvature. If you imagine, well, let's just take like the side view. If you're at the North Pole in our globe analogy, and you wrap the radius of a circle, it has to hug that curvature of the globe. So you just have an R that's the same as the old R. Remember, from that thought experiment, that didn't change. But here, this circumference, call it circumference primed, is less than if you just had the same R out here and you had whatever circumference that would make, call this like quote unquote regular circumference. This curved space circumference is less than the one that's in two-dimensional space, remaining flat, which means this isn't the curvature. This kind of curvature isn't the one that matches that situation of relativistic rotation. But there are other options. This is a picture of hyperbolic space, or negative curvature. And if you plot out a triangle similar to on the sphere, what you end up getting, I'm going to probably butcher this, but you end up getting a triangle that looks pinched in at the corners. And these are all something like 45 degrees instead of all being 90. And of course, 45 times 3 is 135 degrees, which is not 180, which a triangle should be. Now, for that rotation instance, if you set a fixed center of a circle and went out some equal number of units in all directions, you'd get some weird looking thing. That's a very bad drawing. And now we can think about our this is the same R that we've always been talking about. And let's call this circumference double primed. And it turns out that that will be greater than the circumference we decided to do green. I decided to do green. What we would call quote unquote original circumference. So this kind of curvature, negative curvature, does reflect what's happening in that relativistic rotation example. This might be a good time to pause and take stock of what's going on here. So first, eyes on the prize. Einstein's goal is to develop a theory that accommodates special relativity and still explains Newtonian gravity. That is, when you solve it for these quote unquote regular situations, it can be used to derive the Newtonian theory of gravity that we all know and love and had relied on for so long. And he's operating on the assumption, under the equivalence principle, that acceleration and gravity in essence mean the same thing. And then, the other big thing he's working with from special relativity is nothing is faster than light. So this idea of instant action at a distance isn't going to fly. And of course, what's empirically known is Mercury precesses, and this is a problem for Newton, but an opportunity for Einstein to prove himself right. By the same token, Einstein's theory can predict. Now, at this point, where I'm at in the story, he doesn't have this number yet. But the idea is he's going to be able to generate it if he can find the right equations. And when he does, as you already know, he's gonna put out there like a carrot for experimenters. Like, here's the number, here's the amount of bending. On the next eclipse, you guys go find it for me. So looking back over all this, where we're at in this little story is we've teed up like the next part, which is basically he needs new math. Because the last thing on this list of bulleted kind of facts we're dealing with would be Euclidean geometry cannot describe certain realities of space and time. And that leads to this need for new math. So for this new math, Einstein's got an ace up in the hole. He's got an ace up his sleeve. And he had this buddy at Zurich Polytechnic named Grossman. He would take notes for him on his math classes that he skipped. And in 1907, a little bit of timeline, 1907 is when Einstein has the happy thought, quote unquote, about the window washer falling off his ladder or perch. And this leads to the equivalence principle. And then he's in Prague for a while, but then he comes back to Zurich in 1912. And he thinks it's about time to start taking up the problem of general relativity, or the gravity problem as he would have put it at the time, in earnest. He's taking it very seriously. So he sends a letter to his old school buddy, Grossman, and this is a real quote. He says, "Grossman, you've got to help me or I will go crazy." And Grossman's like, "Yeah, no problem, buddy. What are we going to do?" And what they do is the same thing any other scientist might do. They go read the literature. And Grossman knows what's up with curved space geometry. And he goes and he looks into it and he comes back to Einstein. He's like, I think this thing you're talking about, these problems you're describing to me, this is a Riemann problem. Like, this dude Riemann has the curved space geometry that I really think is going to apply to this. And once Grossman pointed Einstein in this direction of Riemann and also Ricci, what's called tensors, these geometries that they were developing, Einstein was down a rabbit hole, if you will. And what we see here is what's known, it's like this object of lore now. It's been picked over by historians to get a window into Einstein's thinking at the time. It's known as the Zurich notebook. And what's he doing in this thing? Page by page, he's trying out these different, generally covariant metric tensors. That's a lot of big words, which is, at heart and most basically, it's a set of rules for curved space from which they're general, right? And no matter where you apply them in space, you're going to be able to make a derivation that matches the reality you see in the universe. And also notable by now, or at this time, is, Einstein's kind of famous for I don't know if not respecting mathematics is the right way to put it, but he's known as someone who, needs help in that area. But this is like an intensely generative time for Einstein when he's thinking about the mathematics and the physics at the same time. And he's come to totally respect it if he didn't before. And he sees how math can be generative of a physics theory. And really, like at its very core, the general theory of relativity cannot be separated from the geometry, right? But ultimately, this time in Zurich, the thinking in the famous notebook, hanging out with Grossman, it proves it's not the end. They don't quite pull it off. They don't find these equations that they're looking for. They're close, which leads them in, I think, 1913 to publish like a sketchy version of general relativity. And they put out this paper. It comes to be known as the Antwerp theory, which literally translates to outline. They're outlining like the promise of general relativity, and they're signaling to the world that they're hot on the trail. But it's just not there yet. It's just not there yet. And then Einstein is lured away to Berlin. He goes to work in Berlin at the behest of Max Planck and others. So he's apart from Grossman now. But he obviously never stops thinking about general relativity. And, you know, in the couple of years after 1912, from Zurich, moved to Berlin, he's refining it, he's working on it. And by the middle of 1915, he gets it to a point where he's gaining confidence now. And he goes and he gives a few lectures. And he meets this guy, Hilbert, and they really hit it off. And yeah, he's got a great looking hat, but Einstein kind of sees in him a kindred spirit, and I don't know, it's almost like he spills the beans to this guy, and he tells him like everything he's thinking about general relativity. And of course they didn't like have a concrete conversation about this, but then Hilbert is going to go off, and he's coming from the math side, and he's gonna like work off in isolation. He's gonna work really hard on developing the general theory of relativity for himself, which, you know, is kind of weird. And for the next few months, through the rest of 1915, there's a series of letters back and forth between these guys, and like my modern take on it is like they're frenemies. Like they're kind of using friendly tones in the letters, but if you read between the lines, they're kind of like pushing and prodding each other, and kind of jealously trying to get to the finish line before the other one does. But, you know, I mean, you know how that ended. Einstein's famous, and I'm guessing maybe today is the first time you ever heard Hilbert's name. So, as they say, the cheese stands alone. Einstein got there first, and it came at the end of this like remarkable 4-week period in November 1915. By the fall of 1915, Einstein, he's living in this incredibly complicated set of circumstances. He's alone in an apartment, like a bachelor pad in Berlin. He's estranged from his wife. The marriage is about to end. Seems like everybody knows it. His kids, not for no reason, are fed up with him. World War I is raging, and he's doing work in the capital city of a country he feels no national pride for. He's a devout pacifist. He's not a politically popular figure. He makes notes or writes postcards to people, kind of saying he forgets to feed himself. And yet, in November, he does these 4 lectures, this series of 4 weekly lectures in a row throughout the month at the Prussian Academy of Sciences in Berlin, where he brings it home. He figured it out, but it wasn't like he was sitting on it and then he's like, putting the fine points on, and then he's like fully prepared to lecture. He's, giving a lecture in the first week of the month, and then he's feverishly going back to the chalkboard alone in his apartment, working out the next bit. Like he's laying the track as he's running down the track. And then, and then it happens. In the third lecture, he really goes for it. He stands up in front of everybody and he shows them how he can derive from his theory a precession of Mercury that's 43 arcseconds per century. Nearly dead on. And then, at the same lecture, he goes through a new derivation for how much light should bend near the influence of the sun's gravity. And he audaciously puts this number at 1.7 arcseconds, which of course turned out to be right. So here we are, back at the start, or back at the end of this story, and you'll remember that this headline came in November 1919, 4 years after this. Actually, there was a plan for a 1914 expedition to photograph an eclipse, but it failed because World War I broke out. That turned out to be lucky because Einstein's original prediction for bending was about half as much as he ultimately calculated. The ubiquitous analogy or pedagogical device you always see about general relativity is this picture, or one like it, where if you're live in a room with a teacher, it's like the idea that you set a bowling ball onto a lycra sheet and it sinks down. And what this does is it conveys to you like what the warping of space-time might kind of be like. But like any analogy, it has its limitations. Like, you all know that in a real room with a real bowling ball on a spandex or lycra sheet, you're just making something longer. But the actual idea in play is that space and time themselves are warped. And, you're probably going to spend your whole life trying to wrap your head around that one. But I'll close with what's probably the most famous summation of the relativity theory. John Wheeler, Feynman's thesis advisor, puts it this way: matter tells space-time how to curve, and curved space tells matter how to move.